Good morning. Small audience today. Is it because of the snow? Since we concluded hydrodynamics last time, there is a quiz. So if you log in on the web page of the lecture, you should be able to find that quiz. Do you? Have you found it? Please answer it. It should be available between 9:15 and 9:30 today. This does not mean that you should take a quarter of an hour, but that this quarter of an hour is an upper limit. And there are questions with one correct answer. There are questions with more than one correct answer. Please take this into account. So where are you? Are you done? Are you getting bored? All right. As I said, the quiz is open until 9:30. So if you like, you have a chance to continue with that. Nonetheless, let us get to the lecture now. So apart from my repetition of the Rayleigh-Taylor instability and the convective instability, we started with plasma physics last time, and I first wanted to present some scales that characterize a neutral plasma. First of all, we defined what a plasma is, what a neutral plasma is, and then looked at the effect that a single point charge has in a neutral plasma. And we saw that due to shielding, that point charge has no Coulomb potential anymore, but a Yukawa potential, where a certain length scale appears that is characterized by the Debye wave number. And with that, I wanted to restart again. So we had derived an equation for the Debye wave number, which was (4 pi NE bar). NE bar was the average unperturbed electron number density times E square over kBt. And we convinced ourselves that this expression here on the right-hand side now has the dimension of 1 over squared length, so we have to take the square root here. That was the Debye wave number, and we said, okay, let's turn it around and get a Debye wavelength. Okay, and now with that wavelength, we can also define a time scale. And that time scale is characterized by, first of all, the Debye wavelength, and second, by the average, that is the RMS velocity of the electrons. Okay, so it's a time that tells you how long it takes for an electron, on average, to cover the Debye wavelength. All right, so that would be lambda d squared divided by v square average square root. Now, what is the average velocity? I'm taking the average velocity squared along one spatial direction. So then I know that must satisfy this relation here due to the equipartition theorem, right? Because then along one direction I have one translational degree of freedom, so the average energy must be kBt over 2 in a thermal plasma. And therefore I can continue writing first of all the inverse Debye wavelength, or the inverse Debye wave number squared. That's this expression here, that's lambda d squared. And then we have 1 over this expression here for the average v square. So that is me divided by kBt to the power of a half. All right, and you see, obviously, the temperature drops out, and we get me divided by 4 pi NE bar E squared to the power of a half. That's now a characteristic time scale for the electrons to run over the Debye wavelength. And now the important concept is the plasma frequency, right? That's the inverse of this time scale. And you see that this is just the square root of 4 pi NE bar E square divided by ME. That's an important scale, right? So now we have two things. We have an important length scale. That's the Debye wavelength. And we have an important frequency. That's the plasma frequency. And as I told you last time already, this is important because if you perturb the plasma with a frequency that is much higher than the plasma frequency, the plasma will not be able to react. And then the plasma is essentially transparent to incoming electromagnetic radiation. If you insert numbers here, you see that's 56 kilohertz if the electron number density is 1 per cubic centimeter. 56 kilohertz. What kind of radiation is that? Electromagnetic radiation with 56 kilohertz. Is that visible light? X-rays? What is it? How do you calculate the wavelength for that? Take the speed of light and divide by the frequency, right? This is kilometers wavelength. These are very long wavelength radio waves. Okay? Well, of course, if the plasma becomes denser, then the plasma frequency increases. But typical electron number densities, for example, in the plasma in a galaxy cluster, are on the order of 100 maybe. So then you have 560 kilohertz, and instead of kilometers wavelength, you have 100 meter wavelength. And then you need to take account of redshift and so on and so forth. Right? So this is long wavelength radio waves. All right. Maybe one interesting aspect, maybe not interesting, is that E squared divided by ME is C squared times the electron radius, right? The classical electron radius. So if you want, you could express this also by the classical electron radius and the speed of light. I found this illustrative but not very useful, but I wanted to mention that. All right, these are the scales that I wanted to introduce in the first place. And now we have another length scale, which is the mean inter-electron separation. And that's also an important scale because that characterizes the plasma microscopically. Right? This length scale characterizes the length scale for electromagnetic effects in the plasma. But microscopically, we define another length scale by saying within this length scale R bar, with a given electron number density NE bar, I want to have one particle. In other words, I'm searching for a length scale such that a sphere with that radius would contain on average one electron, which of course leads you to R bar is 3 over 4 pi NE bar to the power of a third. Okay, that's the microscopic scale. And now with that scale and the Debye wavelength, I want to characterize what we call an ideal plasma. And for that, I'm starting to relate the average electrostatic potential energy here. And I'm using R bar, and I'm using the Coulomb potential here for reasons, not the Yukawa potential. All right, so that's the average potential energy of an electron in the electrostatic Coulomb field of an ion. Charge number Z. Okay, and I want to relate this to the thermal energy. I want to see which is larger under which conditions. Okay. Now let me just insert the R bar here. So that is ZE squared. Now 4 pi NE bar divided by 3 to the power of a third. That's the 1 over R bar. Divided by kBt. Okay, I don't like this exponent 1/3 here. I would like to have a 1. Obviously, right? Because then I can directly relate this to the biwave number or the biwave length is. But then I need to correct for that by saying I need to multiply this now with the inverse to the power of 2/3, right, to set this straight. But now you see, okay, this is just the square of 1 over R bar. And for the rest I can write this as Z over 3 R bar square divided by lambda d square. Okay? And we call the plasma ideal if R bar is much smaller than the Debye wavelength. In other words, that on the length scale where electromagnetic effects happen in the plasma, there are very many electrons. In other words, the microscopic structure of the plasma does not play a role if we look at electromagnetic effects at the Debye wavelength. Okay, then we call the plasma ideal. In other words, this is the situation in which we can essentially treat the plasma like a fluid. Right? So again, we have a kind of scale hierarchy here, right, where the microscopic length scale is much below the length scale of electromagnetic effects. All right. Good. So now we have characterized the plasma with a set of numbers, which are going to be very important and going to be, which are going to reappear everywhere. And now I'm going to look into electromagnetic properties in the plasma. And you may have noticed in the course of this lecture that this is not a lecture about astrophysical phenomena and how you interpret them, but this is a lecture about methods that you apply in astrophysics. And the spirit of this lecture is that I would like to present to you a set of methods, right, that you often apply if you need to analyze astrophysical phenomena yourself. And so as we go through electromagnetic phenomena in the plasma now, there's also going to be a set of methods that we are going to apply that you find, first of all, in this context, obviously, but also in many other contexts in physics, like response functions and all kinds of things. All right, so let's have a look at electrodynamics. And of course, if you have to do with classical electrodynamics, you start with Maxwell's equations. What else? So, just copying them, and then we see what we do with them. Here's a dot. Okay, these are the equations of electrodynamics in vacuum. Of course, we do not have a vacuum here, right? We want to have electromagnetic waves in a plasma, but let's start with them. So now, what do we do if we want to port these equations into a medium, right? And the rule is always the same. You leave the homogeneous equations as they are, and you change the inhomogeneous equations. And in the inhomogeneous equations, you replace the electric field strength by the electric displacement, the D, and you replace the magnetic field strength by the field H, right? Also the magnetic field. Okay, and D is typically written as epsilon times E, and B is typically written as mu times H. This is one way of doing that. Right? This is one way of relating the dielectric displacement or the magnetic field strength to, well, relating D to E and B to H. But it's not the only one. It's a linear relation, and also we need to say a lot of things later on this quantity epsilon here. And in addition, we typically have that J is sigma times E, where sigma is the conductivity of the medium. Okay, so these are the general replacements, and then you take the two inhomogeneous equations and replace them accordingly. So you leave the homogeneous equations as they are, and instead of the inhomogeneous equations, you write diff D equals 4 pi rho, and you write C times curl H minus D dot equals 4 pi J dot. All right, this is step number one. Now we have Maxwell's equations in media, specifically in linearly responding media. They do not need to respond linearly, right? They could do something else. But we are assuming linear response here. Okay, now what's the meaning of the rho here? It's the charge density, but it's the free charge density. So this is the charge density provided by actual charge carriers minus the polarized contribution. Right? Because due to the exposure of the medium to an electric field, the medium will respond, and the electric field will create a polarization within the medium. And this polarization will give rise to a charge density, as we will see. And this polarized charge density is subtracted from the actual charge density to arrive at the free charge density. And this is the rho that we have in this equation here. Now in our plasma, this means that we have to insert in this equation here rho equals what? What's the free charge density in our plasma, according to the assumptions we made last time? What's the free charge density in a neutral plasma? Ah, come on. Sorry? It will be 0. Right, we started from the assumption of a neutral plasma, right, where all the charges of the ions are compensated by the charges of the electrons. So the free charge density here will be 0. In addition, right, if you expose the medium by to an external magnetic field, the medium will respond to that if the individual particles in the medium will have a magnetic moment. We ignore that here. Right? So in the way how we are going to go on, we will set mu to 1, right, saying that, or assuming that the plasma will have the magnetic moment of the vacuum. Okay, Medium is not going to change the magnetic moment here. Furthermore, we will assume that we will have no free currents. Okay, we will have polarized currents because the plasma will react to infalling electromagnetic radiation. So the electrons will move according to the electric field. But this is a polarized current. It's not a free current. Right? So in this equation here, which contains the dielectric displacement and H, we have the free current density, and that's going to be 0 as well, even though we will have polarized currents here. Okay, so as we move on, we are going to make the following further assumptions, that rho equals 0, which means the free charge density, as opposed to the polarized charge density, which will not vanish. We will further assume that we have a vanishing free current density, and, as we said, we will further assume that mu is 1, saying that for the moment we are going to neglect any magnetic dipoles that there may be in the plasma. Okay. So the set of equations that we are going to consider is the following. We have diff d equals 0, diff b equals 0. We are going to have C times curl E plus B dot equals 0. We are going to have C times curl B, because I'm using this equation here, the other inhomogeneous equation, but with mu equals 1, then minus D dot equals 0. That's the set of equations that we are going to look at. Okay, within the plasma. All right. In addition, then, we will have a look at this relation here, and our target for much of today and probably also next Monday is going to be the dielectricity here. For reasons that will become clear, right? But the epsilon, this is what we are interested in. Why are we interested in that? Because it tells you how the plasma or how the medium reacts to an imposed electric field. So this is what you call a response function in statistical physics. And it tells you how the plasma responds to the electric field that it is exposed to. Okay, now, in addition, we know that I keep mistaking the signs here in this definition of the polarization P. Let's see. I think it's this way. I may have to correct this later. All right. So we have two ways, or we introduce two ways of characterizing the response of the plasma to the electric field. One is by saying, okay, we write the dielectricity here as a response function, or we say the electric field is partially countered by the polarization. Okay, then we apply the divergence to that, to this equation. We know that this must be 4 pi times the free charge density. Then I move on here. Here I have the divergence of the electric field. minus 4 pi the divergence of the polarization. Of this, I know from Maxwell that this is 4 pi times the total charge density. And I'm calling this here 4 pi times the polarized charge density with a negative sign, such that the divergence of the polarization equals minus the polarized charge density. Okay? And then we apply continuity to the polarized charge density. So we say, okay, the polarized charge density will also be conserved as the charge density will be. And so in addition to that, we then know that the time derivative of the polarized charge density plus the divergence of a polarized current density, right? There's going to be an electric field. It's going to disturb the plasma. It's going to polarize the plasma. And of course, if the impingent electric field is time dependent, the polarized charge density is going to change. So there will be a polarized charge density current. And this will obey a continuity equation like that. And so you can write this as a divergence of dt minus dt of the polarization plus the polarized current density. And from that, if we can conclude that the polarized, or if we can assume that the polarized current density has no curl, then we can say the time dependence of the polarization equals the polarized current density. Okay? So, what we are going to do now is the following thing. We are going to target epsilon. We want to know what epsilon is, right? We want to know how the plasma responds to an electric field that it is exposed to. That's the goal. We want to know what epsilon is. In order to find out, we will have to walk a long way. First of all, we will rewrite this equation in an appropriate manner, and then we will use kinetic theory to express or to write an equation for either that quantity or that one. Doesn't matter. But then we will use this equation here or that equation there in order to relate kinetic theory to the polarization. Okay? So our way will be twofold, right? We will walk two different ways. The first one is we will rewrite this set of equations in terms of epsilon, just to find a general expression for the epsilon, and use Maxwell's equations to say what the conditions on epsilon are such that electromagnetic waves can propagate. That's one thing. The other thing is that then we will use these relations here, or either of these, plus kinetic theory, in order to find a specific expression for epsilon. That's the goal. Now, let's start with that. Let's first have a look at this expression here. The first question is, what is epsilon? Is this a scalar, or what is that? It could be a scalar, right? That's what you are probably used to, and that's the boring case. The much more interesting case is that epsilon is a tensor. And we need something that maps a vector to a vector, so either this must be a scalar or it must be a tensor. When do we need a tensor? Whenever the medium has its own idea of what good directions are. Right? Now, if we have a thermal plasma with no further constraints, we would not need a tensor actually. Nonetheless, it's good to start with a tensor here because later we will also speak about the electromagnetic properties of magnetized plasmas. And then, of course, a magnetic field imposed on the plasma will create a further direction in the medium, which may or may not coincide with the direction of the electric field. But then the plasma will have its own idea of of its principal directions, and then you will need a tensor. So we'll start with a tensor right away. Now, you can phrase this equation in configuration space such that d and e and epsilon are functions of t and x, the time and the spatial position. Or you can write them in Fourier space. Right? You could write d and epsilon and e as functions of omega and k. Now, what is better? Does it matter? Well, it matters a lot actually, because if you start with writing down this relation in configuration space, you need to take account of continuity of causality. Right? The medium cannot respond before the reason for the response. So you need to take into account that the response of the medium, let's say at time t and position x, must depend on all effects that an electromagnetic field had in the past at a certain distance, right? At a retarded distance. So you need to actually write this as a linear superposition of epsilon of t prime and x prime, and now you need to integrate over dt prime and tx prime. All right, and of course t prime and x prime must be related to t and x by the retardation conditions. So you would generally introduce here the response of the medium, the dielectricity, at t minus t prime and x minus x prime, and you will multiply this with E taken at t prime and x prime, and you will integrate over all times in the past. So I should specifically write that you take a time integral here from minus infinity to 0 or to t, and you integrate over all positions x that can be reached, x prime that can reach the position x within that time. But now you see this is a convolution. This is a convolution in configuration space. Of course you can start here and this is all fine. Right? But if you go to Fourier space, the convolution will turn into a product, right, by the Fourier convolution theorem. So it's much easier and much more appropriate to start in Fourier space in the first place. Okay? So this is the reason why we write this equation here in this way. And I'm asking for your permission to not distinguish the Fourier space quantities from the configuration space quantities, because otherwise the notation gets really clumsy. So we are going to work in Fourier space, right, for that reason. All right. Have you heard of the Kramers-Kronig relations? Did anyone tell you in electrodynamics? These are relations between the real part and the imaginary part of epsilon, which are created by the causality condition. Right? So if you wish to start in this way here, you need to make sure that the epsilon satisfies the Kramers-Kronig relations in order to express causality. But this is just a side remark. All right, so we start here by this linear relation in Fourier space in order to respect causality, right? We should do that. But then, of course, we will also have to port the rest of our equations to Fourier space as well. So how do we do that? We decompose this set of equations here into plane waves. In other words, we assume that we decompose E and B into plane waves. We can do that because they are linear. And then write the equations simply in terms of the Fourier component. So what does this mean then? In addition to that equation, we are going to have k times d equals 0, k times b equals 0. That's just a consequence of the vanishing divergences. And here you see already that the dielectric displacement will be transverse, right? As will be the magnetic field, because they are both perpendicular to the wave vector. Last time I told you we will study longitudinal electromagnetic waves as well, right? This is because even though the dielectric displacement will be transverse, the electric field doesn't have to be. Okay? So, next, you see if I decompose E and B into plane waves and I take the curl, I'm getting an IK cross. If I take the time derivative here, I'm getting a minus I omega. So now this sign and that sign will flip, right? Because omega and k have different signs in the Fourier phase. So then we have, and of course I will drop the factor I, right? Because I can cancel it. So C times k cross E minus omega times B equals 0. That's what is left over from this homogeneous equation. And then the rest is CK cross B plus omega times D equals 0. These are the Maxwell equations that we have to solve. In addition, we make the assumption of linear response, that is, we can write in Fourier space, D is epsilon times E. Okay, good. Let me very briefly add another remark about these longitudinal electromagnetic waves, right? They will play a role no matter what. But if you start from this equation here, and you write the linear response in there, you see that this is gradient epsilon times E plus epsilon times the divergence of E. Right? And if you translate this to Fourier space, you see that this does not imply any longer that k times E should be 0, if the dielectricity is space dependent. Okay, so this means that if the response of the medium is spatially dependent, if that has a gradient, then electromagnetic waves are no longer transverse in the medium. Okay? And then we need to consider longitudinal waves as well. Even though the dielectric displacement here is transverse. Okay, now we do one more thing before the break, and then we have the break. Okay, I'm taking the curl of that. In other words, I'm multiplying this with a vector product with k. So this gives me ck cross k cross e. Okay, this would be equal to omega times k cross b. But I know what k cross b is, right? So this is omega times. Now k cross b is minus omega divided by c times d. Okay? Now we have a second expression for the relation between d and e. Let me finish that here. Now I'm going to use the Grassmann identity, right, which allows me to take this double vector product here and decompose that into two scalar products. Now what is that? First of all, let me divide by c and then write with the Grassmann identity scalar product of k times e times k minus k squared times e. Right? This is the result, or that's the statement of the Grassmann identity on this double vector product. And this is minus omega squared divided by c squared times d. Okay, but now you see we have one relation here between d and e, which is required by the Maxwell equations. And we have another relation between d and e, which we demand, right? This is our demand of linear response of the medium. Okay, now we have to marry both. But that's something we do after the break. Okay? Right. Ready to go? Is that loud enough today? Stronger electric field? Let's try like that. Okay, so that's where we were, and now of course we need to combine these equations, but remember where they are from. Right? The second is Maxwell. The second tells you under which conditions electromagnetic waves can propagate in the first place. The first is linear response theory. The first is our wish. The second is a commandment. Okay. Now let me write the second equation in tensorial form. First of all, I'm changing the sign on both sides. And then I'm writing the first term here, which now has the positive sign, a bit artificially with the unit matrix here. No harm, right? And let me write the second as tensor k cross k, or k times k with the tensor product, times E. That's the same thing as this term, right? Because if you multiply this out, you will have a scalar product between k and E from here, and then the direction will be given by k. So this is the same as that with the sign change. Are you happy with that? Are you disturbed by that? So let me write this in components. So I'm looking at this term only now, right? If I take this object and I want to have its I component, what is that? This is Ki Kj times Ej. Okay? So this is Ki Kj times Ej. And by definition of the tensor product, this is the Ij component of K tensor K. All right? Disturbance removed. We need this, right? We need to write this in tensorial form here. And since I don't like indices, not at all, I'm doing it like that. Okay. So I can write this as k squared times unit matrix minus unit vector k, that's the k with a hat, right? That's the unit vector into k direction, times E. Okay, so now I have this equation, Maxwell's equation, in manifestly tensorial form on the right-hand side. And of course, I want to write omega squared divided by c squared times epsilon times E on the left-hand side, right? Because we have demanded this linear response relation there. All right, now let me bring this together and write unit matrix minus k times k minus omega squared divided by c squared k squared times the dielectric tensor epsilon times E equals 0. All right? Now we have a combined equation made from Maxwell's equations, the commandment, and the linear response requirement, which is our wish. Okay? Now, the same arguments as we have used them, for example, in hydrodynamics apply here as well. Right? We want to have a non-trivial, in the best case, non-trivial solution of that equation. That's an algebraic equation. Why is it algebraic? Well, because we made Maxwell's equation algebraic by decomposing them into plane waves. So we have a linear algebraic equation. We want to have non-trivial solutions. What does this mean? The determinant of the matrix in that equation must be 0. Right? Because if it were not 0, I could invert the matrix and then the trivial solution would be the only one. Not good. Right? Okay, so this means that we have a propagation condition. For the electromagnetic waves in the medium, and this says that determinant of 1 minus k times k minus omega squared divided by c squared k squared epsilon, that this determinant must vanish. And what does this give you? It gives you a dispersion relation, right? The relation between frequency and wave vector. And exactly in the same manner as we use dispersion relations in hydrodynamics. Right? We will see where is the frequency squared, positive or negative. Right? Because if the frequency squared is positive, you will have propagating electromagnetic waves. And if the frequency squared is negative, they will die out and will get absorbed. Okay? Same procedure every time, right? You linearize the equations, you set up a dispersion relation, you check the dispersion relation for negative frequency squared. If you look for the evil, right? If you look for the good, you check them for negative frequencies, positive frequency squared. Okay. Good. All right. Now comes another methodical aspect, namely the concept of a projector. Have you come across a projector? Of course, yes, here is one. A projector is an operator that squares to itself. No more, no less. Projector P squared equals P. Why is that so? Well, once you have projected one thing and you project again, you don't want to change that. Okay, so all right, now I'm going to introduce two projectors. One projector into the subspace of 3 space. Right? We have a 3-dimensional configuration space. I want to project into that subspace that points along the propagation direction of the electromagnetic waves. I want a projector on the wave vector k. I call this the parallel projector. And I claim that this is just k times k, or k hat times k hat, where k hat, again, is the unit vector into k direction. This is a projector on k, you see, because if you apply the parallel projector to the k vector itself, right, you get, again, a scalar product between k hat and k, which will give you just the absolute value of k times k hat, and this is vector k. If you take any other vector, right, that has a component into the k direction and a component perpendicular to it, then the same operation will kill the component perpendicular to k. Okay? Is pi square equal to pi parallel squared? Is that equal to pi parallel? Well, that's this thing. Now, by the rules of matrix multiplication, I need to take the scalar product of these two. And then the vectorial product, or tensorial product of these two. Right? So k times k with a hat is 1 by definition. So this is times 1, and that's the parallel projector again. So it satisfies our only definitive criterion for things being projectors, and therefore we can address this as a parallel projector here. All right, now let's take a perpendicular projector. I want to have a projector as well for projecting perpendicular components out of a vector. Perpendicular now to the propagation direction, and this is simply 1 minus the parallel projector. And if you remove the parallel part, well, then you will be left with the perpendicular part. If you apply this to K, obviously the first part will give you K. The second part will give you minus K according to this calculation. So this will be 0, right? So everything pointing in K direction will be projected away. Does it square to 1? Well, if you square this, you get 1 times 1, that's 1. Then you get minus pi parallel. You get minus pi parallel. And you get plus pi parallel by squaring pi parallel. So the square of this will again be 1 minus pi parallel, and you're fine. Okay, so this is the perpendicular and the parallel projector. All right, I need these in order to project out longitudinal and transverse components of the dielectricity. And these will be scalars. Okay, these will be scalar functions, and the way how we define them, I'm going to show you now. But before we do that, let me introduce a scalar product for matrices. Have you seen this? Suppose you have two square matrices A and B. So they could be from Cn times n. You introduce a scalar product between A and B by taking the trace of A Hermitian conjugate times B. If you look at that, you find that's a scalar product between such matrices. And I use the scalar product now for doing what you always do with the scalar product, namely for projecting out components. Right? So, if you take the trace now of the parallel projector if you take the scalar product now of the parallel projector with itself, that's going to be the trace of pi square parallel. But pi square parallel is pi parallel. So there's just the trace of pi parallel. If you take the trace of pi parallel, that's just the scalar product of k hat with itself. If you write this in components, you see this instantly. Right? So that's going to be 1. That's nice, right? We have a unit projector in the sense of the norm that is induced by that scalar product there. But if you take the scalar product of the perpendicular projector with itself, this is, of course, the trace of the perpendicular projector itself, because any projector squares to itself. But now if I take the trace of that, you see that's 3 minus 1, that's 2. So the projectors are obviously not normalized. Right? And if I later project out longitudinal and transverse components of the dielectricity tensor, I will have to take into account this, the fact that this has a norm of 2. Why does it have a norm of 2? Well, because it projects on a two-dimensional subspace, right? I mean, the parallel projector projects on an axis. The perpendicular projector projects on a plane. And because the dimension of that subspace that it projects on is 2, it has norm 2. So we need to take this into account, not in order to count these dimensions twice. All right. So with this definition of a scalar product between matrices, we can now define what we mean by a perpendicular and a parallel component of the dielectricity. Right? This is going to be 1/2 the trace of epsilon times pi perpendicular, and this is going to be the trace of epsilon times pi parallel. And then we will be able to write the complete dielectricity tensor as epsilon times pi perpendicular plus epsilon times pi parallel. That's what we are going to do. But beware, there is danger around the corner. These two projectors are not a basis for epsilon. Okay? Obviously, epsilon as a usually symmetric tensor must have, in 3 dimensions, must have 6 components, 6 independent components. So the dimension of the tensor space where epsilon is taken from must be 6. And we have 2 basis elements here. This cannot be a basis. Okay? So there may be cases, for example, where the dielectricity tensor contains antisymmetric components, for example. Or where the dielectricity tensor has its own direction imprinted. And then decomposing it into these 2 projectors with respect to the propagation direction of the electromagnetic wave will not suffice. Right? So we can do this here for the simplified situation where the plasma does not have its own direction imprinted. Yeah. I'm sorry. Yes, that's what I meant. Thank you. All right, so that's the recipe that we are going to follow, right? But be aware of its pitfalls, right? We are currently now dealing with a plasma that has not its own direction imprinted. In that case, we can indeed decompose the dielectricity tensor uniquely in that way here, uniquely except for rotations about the k-axis. Okay? But once we introduce a magnetic field, we will have to do more than that. Okay. So let me now return to this equation here, using that decomposition of the dielectric tensor. Then I can write, first of all, pi perpendicular, right? You recognize pi perpendicular here. Okay, it's pi perpendicular minus omega squared divided by c squared, k squared, epsilon perpendicular pi perpendicular plus epsilon longitudinal, pi longitudinal times E equals 0. Now, of course, you can combine things and write pi perpendicular times 1 minus omega squared c squared k squared epsilon perpendicular. Remember, epsilon perpendicular is a scalar now. Right? That's a scalar function. So I can compare this to 1 here. Okay, but that's the transverse part of our response function. And then we have minus omega squared divided by c squared k squared epsilon parallel pi parallel times E equals 0. So now, what have we done? We have simply split our propagation condition into a longitudinal and a parallel part. When is this useful? When we want to study separately how longitudinal and transverse electromagnetic waves are going to propagate. So suppose I have a transverse electromagnetic wave impingent on the plasma. Then it will project to 0 with pi parallel, pi parallel here. So for longitudinal waves, we have longitudinal, we have transverse waves. Of course, you can have mixtures of both, right? You can separate them because you can linearly superpose them. So in the longitudinal case, we will have pi perpendicular times E equals 0. And in the transverse case, we will have pi parallel times E equals 0. And then you can simplify the above propagation condition and can say for longitudinal waves we simply have omega square divided by c square k square epsilon parallel equals 0. This is our propagation condition. And since setting omega to 0 or k to infinity doesn't make any sense, the only conclusion is longitudinal waves are possible if epsilon parallel is 0 itself. And the condition under which this can be, we'll see. All right, the other one is 1 minus omega squared divided by c squared k squared epsilon perpendicular is 0. That's the propagation condition for transverse waves. Okay. If you apply this to vacuum, you see, okay, in vacuum, longitudinal waves are evidently not possible. That restores the common knowledge. And for transverse waves, well, epsilon transverse is going to be 1, and then this restores the dispersion relation for electromagnetic waves in vacuum. Right. K squared is omega squared over c squared. Okay, so here we have epsilon parallel equals 0 as a propagation condition for longitudinal waves, and here we have epsilon perpendicular equals c square k square over omega square for transverse waves. These are the results from Maxwell's equations, assuming linear response, decomposing the participating functions into a parallel and a transverse part. Okay? Now we know a lot more, right? And we know exactly nothing. Right? All we have done is rewritten the propagation condition in different ways. That's lovely, and it allows us to keep order, right? But since we have no idea what epsilon is, we can't continue now. So now we will have to look at epsilon and see what we can say about the dielectricity by other means. Right? Okay, do you have questions up to this point? Of course, you can write all of these relations here with indices. This creates a lot of mess, right? And then you mess up the indices, and then you find different things and so on. And my experience is that writing things in indices just tries to make, or just makes the physics of the equations more opaque. All right. So now we know what the propagation conditions are. Now we need to see what is epsilon. And for that we need to look at kinetic theory, because we want to know how does a plasma react to a force, an electromagnetic force applied to it. Okay. Let's start with a phase-space density F. And what I mean specifically is the phase-space density of electrons. Why am I doing that? Because the electrons are so much more mobile than the ions are, that it is sufficient to look at the response of the electrons alone. Right? The ions have at least a factor of 1800 more mass than the electrons have, and therefore typically the response of the plasma ions, right? The ion component of the plasma, is negligible. So let's do that and say that's the phase density of electrons. And then I'm using the Liouville equation for the time evolution of the phase-space density. Okay, so this means that I'm starting with that. And remember, you get the Liouville equation under the sole condition that the dynamics of the particles involved is symplectic. It doesn't even need to be Hamiltonian, it's sufficient that it's symplectic. All right, so under very general conditions, this is true if you can ignore direct collisions between electrons. Okay, so let's assume that, and this will be, or this will lead to the response function for what is called a collisionless plasma. Okay? All right, so what is this? That's the partial time derivative of f now, plus velocity times the gradient with respect to x applied to f, plus p dot times the gradient with respect to p applied to f equals 0, right? I'm just writing out the total time derivative, and I'm using that f is a function of time and the phase-space coordinates x and p. And then I've written down just the total time derivative here. Okay. Then, remember, we are looking at a linear response function. Right? How do we know? Well, we said we want to have dielectric displacement equal epsilon times E. So we suppose a linear relation between D and E. So now we need to linearize this equation. In other words, same procedure as every year, right? We decompose F into an unperturbed density F0 plus a perturbation, and then we linearize in the perturbation. Okay, so now F will be F0 plus delta F. And we are assuming that on the unperturbed plasma there are no external forces. So this means that I can write a separate Liouville equation for F0 alone. And this looks like that, right? No external forces. All right. In addition, I have the complete Liouville equation. For the total phase space density F0 plus delta F. Now, of course, both must be true. And this means that I can first of all write dt delta F plus V times gradient delta F plus P dot times gradient P, of what? See, if I assume that the that the unperturbed plasma is force-free, then the force itself will already be a small thing. Small quantity, I should say, to be less sloppy. So I need to apply the P gradient here to F0, but if I applied it to delta F as well, I would add a term that would be quadratic in the perturbations. Not good, goes away. Right? So the Liouville equation that we have to solve is this thing here. And it is linearized as is appropriate for our assumption of linear response, or our requirement of linear response. Okay, now what is P dot? If you have an incoming electromagnetic field, what is P dot for an electron? Electromagnetic wave. Force on, P dot is force, right? Force on an electron. Tell me. Come on, yes. The Lorentz force. Could you go on? Electron, right, minus E. And then? And the electric part? That's the magnetic part, that's fine. So we have the Lorentz force. Well, the magnetic part is down by a factor of V over C. But I have a better argument for throwing that away, namely the following. Suppose you have an unperturbed plasma distribution F0. Then the gradient with respect to P of F0 must be parallel to the velocity itself. There are many reasons for this to come out that way. First of all, if F0 is isotropic in the momentum, then it can only depend on the absolute magnitude of the momentum, but not on its direction. And if you take the momentum gradient of an absolute value of the momentum, it will be proportional to the momentum itself. That's one argument. The other one, equally valid, is that in an isotropic unperturbed plasma, there is no preferred direction. The only direction occurring in the momentum gradient of F0 is P itself. But I find the argument that F0 can only depend on the absolute value of P or on P squared the most convincing of them, right? Okay, but if this is the case, then gradient P of F0 is parallel to V. The magnetic part of the Lorentz force is perpendicular to V. Since we need to take a scalar product between both, that goes away anyway. It would also go away for non-relativistic motion, but you see here that it goes away even for relativistic motion, if you can assume that F0 is isotropic in the momentum. So, isotropy in P, I mean. All right. So what does now our Liouville equation for delta F look like? It simply looks like that, right? And the magnetic part of the Lorentz force is gone. Now we have linearized our equation. Now, according to the usual cookbook, right, what do? We have linearized our equation. We decompose the perturbation into what? Plane waves. Yes. Yippee, let's do that. What do we have here? Minus I omega delta F. Again, I'm committing the, at least felony, to write the same symbol for configuration space and Fourier space quantities. Forgive me. Plus I times V times K. What is this now? That's the K vector of the perturbation. Delta F. Careful, right? This is not the K vector of the electromagnetic wave, it's a different thing. All right, delta F, plane wave, minus E times gradient P F0. F0. That's not the perturbation delta F. Okay, but now, miracle, we have an algebraic equation. Not a miracle at all, right? We turned our differential operators to algebraic operators. But this, we can now simply solve for delta F. And what do we get? Delta F times I times Vk minus omega equals small e, large E, gradient P F0, and therefore delta F is small e, large E, momentum gradient of F0, divided by I times Vk minus omega. Nice, isn't it? Notice one thing. We decompose delta F into plane waves in configuration space. We did not decompose delta F into plane waves in momentum space. But delta F is a function on phase space. Okay? So we have only decomposed the spatial dependence into plane waves, not its momentum dependence. All right. Now, how do we move on? I don't want to do this today, but here's the recipe for next Monday. now we have a perturbation of the phase space density in the plasma caused by the electric field E. And of course, as it has to be, it's linear in the unperturbed phase space density of the plasma. So if I now want to know what is the polarized charge density, the only thing I need to do is that I need to multiply minus E as a charge for any electron times the momentum space integral over delta F. That's the polarized charge density now, right? It's caused by the fluctuations in the plasma spatial density. And the spatial plasma density is the momentum space integral over the fluctuation, delta F. So now I know what rho pol is. I also can write down an equation for the polarized current density now. Same thing, right? This is minus E times the momentum space integral over delta F times V. Okay? The individual electrons moving with velocity V are going to carry the charge minus E, and their spatial number density is the momentum space integral of delta F. But now you see, we had these relations, right, that the polarized current density is dTp. Right? It's the time derivative of the polarization. All right, but if I perturb the medium with a periodic, if I perturb the plasma in a way that I can decompose into plane waves, then of course the P itself will also be a plane wave with the same frequency. So then in Fourier space, I can write J pol equals I omega P. Okay? But then we are there, right? Then we can say, okay, I can use this equation to solve for P. I can use it together with that equation to relate kinetic theory to the polarization. And then I can use D equals E minus 4 pi P in order to relate D and E. And that will give me, finally, the dielectric tensor. Okay? So that's going to be the program. Now we have the phase space perturbation of the electron density. We can create this to the polarized current density. We can relate the polarized current density to the polarization and the polarization to the dielectricity. And this will give us the epsilon. This will be the result will be the so-called dielectric response function of a collisionless thermal plasma. Right? It's collisionless because of that. It's thermal because we have assumed that the plasma components have a certain temperature, and it's not magnetized yet. Okay, and that's where we are going to restart then next Monday. Thank you.